Alright, today we're gonna have a lecture on disjoint sets, and surprisingly this is not a communication skill, so welcome to the big leagues, I guess. Okay, I wanted to ask you guys about how much you know math, I guess. Does anyone know what a set is in math? I know everyone knows it, I just want to know if anyone is gonna be willing to tell me. Like, what's the definition of a set in math? Right? So a set is pretty much a collection of distinct elements that can classify it pretty much. And what do you think would be a subset? Like, how would you define a subset? Basically, what's a subset? Right? So a set whose elements are, all of its elements are part of another set, right? What's a superset in that case? Everyone knows what a superset is, why did you just say it? Come on. I'm not gonna pick anyone, you guess. Okay, I'm gonna pick someone. What's a superset, Niti? What's a superset? Like, a subset is a set whose all elements are in another set. So in that case, what a superset is another set's all elements, right? And what's the intersection of sets? Right.
Set contain elements which are neutral.
Right? So any union. This is just warm up. Come on, you got this. What's the union of sets? Whichever one answers first, I guess. A set that contains all elements from the different sets, right? And what's a disjoint set? Like, from all what you guys said. What are, like, this is actually plural. What are disjoint sets? Okay, Kala. Sets that don't have intersection, right? So this whole thing that we're learning really doesn't have anything to do with math. I just wanted to build up to the fact that we're dealing with groups that don't have intersection or don't have relations. So think of scenarios where you've had to work with groups that don't have relations. Usually in graph traversal, where you have to group a bunch of things a bunch of nodes that are connected into one, and a bunch of nodes that are connected into a different group, and they're not connected, so they should be considered as different sets. So this is pretty much a study of how we can efficiently run certain operations on such groups. So this is not something new that you figure out or something new that you learn. It's just a way of dealing with such disjoint sets or such unrelated groups. Does that make sense? And for some reason it's also called Unifying, and we'll find that out later, I guess. Okay, so disjoint set that's also called a union-find or merge-find set. It's a data structure in a way. It's a way of storing these separate groups like as efficiently as possible, and it also stores partitions of set into disjoint subsets. There's a whole big set. Let's call it a graph, and it's a way of storing the different unrelated components, unrelated subsets. Like in terms of each other, they're disjoint sets, right? Since they don't have any intersections. It's a way of storing them separately and managing them for better operation, I guess. And it's like this lecture is pretty much going to focus on the set of practices that we can do to make optimal representation of such scenarios and to build such a data structure. All right. What can we do with like what kind of problems call for such implementations, or what kind of problems require separating the different components into different parts? So it can be to keep track of the connected components of an undirected graph. So there's a graph, like I mentioned before. some groups that can be reached from one node can be a part of one group and another group and another group, and and at times when you want to separate them and you want to consider them separately and want to maybe count them or something, this is useful. It's helpful to determine whether two vertices belong to the same set. Like I said, if you can group them separately, you can check if the same element appears in the same group or different groups, and we'll see how we can make that an optimal, how we can implement that in an optimal way. And it also helps to figure out to determine adding an edge between two nodes if it creates a cycle. So if something is in a group, in one group, like if two elements are in the same group, then adding one more edge to them is obviously going to create a cycle, assuming the cycle doesn't already exist. Does that make sense? Because they're already connected in one way, but if we add another extra edge, then that's going to create a cycle. We can determine that efficiently using disjoint set algorithms. I do want to get you guys started on this question. How many of you guys have done this question? I don't know if it was part of the contest or part of the progress sheet, but this is a number of island question where you're supposed to count how many islands there are in a sea of, in a matrix that's filled by water, which is 0, and land, which is 1. So a set of interconnected ones is called an island, and you can assume like the outside of the grid is water, so like the outside of it can be a boundary. So anything that's surrounded by water is called an island, right? You do guys know what an island is defined as, right? It's a land that's surrounded by water. And yeah, like how many of you guys have solved this already? That's it? There's you guys who haven't solved it? You wanna give it a try? Or does anyone want to explain to me how that would work? People who haven't solved it, how would you approach this? Amir, how would you approach this question? Okay, you haven't solved this, huh? So the question is to count the number of interconnected groups.
So the question says I can assume what's outside of the group as uniform. So if I get one, so the ice line, I'll just keep counting the connected ones. And the outside is one island.
How would you do that? How would you keep counting the connected ones? How would you figure out the connected group? Running DFS, right? So, anything more you want to add to that?
Yeah, if I get one, I'll check the neighbors. I'll check both sides. Then, since it's one, like my neighbors are ones, I'll check the income neighbors. And if all the neighbors are 0, I have ones.
Yes, it's a pretty straightforward question, right? So, for those of you guys who didn't hear it, I think what he said is, and correct me if I'm wrong, you can run DFS on each of the elements, and when that DFS runs, it runs through all the connected groups, because it can be like, it's undirected, and if you start from one, you can reach all of them, and once you've collected all those groups, you can count them as one group and then increment your result, and then go to another group, since like already the elements that you counted in that group are visited, you won't need to do the same operation again. When the next time you try the DFS again, it's gonna work on a different group, and you can count how many times you call the DFS, and that would be a result. Does that make sense? That's fine. Okay. And like, should we implement this? I thought like most of you guys had already worked on this, so I didn't think we need to implement it, but maybe we should work on that, right? You guys want to give it a shot? Yeah? Okay, nice. Yeah, with a little modification, you can turn your code into collecting those, like the elements you're traversing into one list or one set, as I did it here, and you can return that as part of your result. That's not difficult, right? So this, in a way, is a disjoint set problem when you're dealing with like storing the different sets, like the different disjoint sets in a way. But would you say this is the most like the most efficient way to store them. Let's analyze this question. Like in terms of time and space complexity, let's analyze this solution. What he just did. So, like, what would be the time complexity of creating like this data set? Abi, like what would be the time complexity of creating the list of groups?
I guess it depends, like, based on the also.
Yes.
The same in my
Right? Like a traversal function, like regular traversal function, right? Like, what would be the space complexity maybe? Like someone else. Anna, what would be the space complexity? What? O of n, where n is each different element, like each, like when you're explaining things in grid, I really urge you guys to call row and column. So number of rows times number of columns would be n, right? In terms of the number of what? Oh, but not necessarily just that. The size of the islands matters too, right? Like the number of ones would be the space complexity. In worst case, it could be of the number of like all elements, which would make it like row times column, right? The space complexity. Time complexity would be the regular day-phase time complexity. Now, this is the creation part of the process. What if you want to check if two nodes, like two indices of the matrix, belong to the same on the same island? Like, let's say you're given two coordinates, and you want to check if they belong to the same island, like they're on the same island. Like, assuming like those 2 points are on an island, you just want to know if they're on the same island. Like, how would you approach this?
Just on the if it is so we just assume there is another.
Look, okay, let me write out the example. So, what you guys did is you generated a list of coordinates, right? Let's call it 0, 1. No, a list of coordinates, right? Like, can someone just tell me an example that they did? Something you printed out? Like, one example that they did there. Just read it out. 0, 0. 1, 0. 1, 1. Like in the same group, right? Okay. 0, 1. Another group? Huh? The same group, sir? 2, 2. Huh? Okay. 3, 3. Huh? 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 Its own group? It's a separate group? You can make it like this, right? So 2, 2 is its own group. Any more to this, by the way? It's enough? We can do this. So, you're given two coordinates. Let's say 1, 1 and 3, 3. And these are your two inputs. Let's call it okay. Let's call it, you're given A and B, which are 1, 1 and 2 and 3, 3. So you want to check if those belong to the same island. How would you do that? How would you approach that? Don't worry about the efficiency. How would you approach it? Think.
I think over one of the set.
And then if I find one of them, I would also put it.
What do you mean one of the sets? How do you know which one to iterate over?
I just have the third one, or I would go until I find one of them. in the
So
set.
run me through. So which one do I look for?
Let's start with 3D to get the
Let's
worst
start with
case.
3, 3.
Yeah, so I would go all over the list.
Yeah, for this one, for this one, for
I
this
wouldn't
one,
find
for
it
this
in
one.
there. I wouldn't find it in there, so I would go to the
You
next
go
one.
to the next one, yeah,
And then I find 3, 3, 1.
right?
Third one, yeah.
Like you found 3, 3,
And then
So-
I look for one in there.
and you limit your scope to this list, right?
Yeah.
And then you look for 1, 1 in here. And since it doesn't exist, it's not in the same island. That's fine, right? Well, how can we make this better at least? At least the search of 3, 3, how can we make it better?
Well, we could search for both, whichever one we find first.
That's also an option. Any other, like what's the time complexity of finding 3, 3 in this case?
And the
All the elements, right? Worst case, we're going to find it at the end, so it's going to be all the elements. But how can we minimize that maybe? Like what can we modify on this to make it like that? I've already hinted to this before. Can we use a set instead of a list?
and then we have
Right. So instead of a list here, we can use a list of different sets instead of a list of lists. Does this make sense? So, is this gonna hurt us in any way, by the way? Like, is there a reason not to use a set? So, the elements are always going to be unique, right? So, you can easily use a set. So, when we're using a set and when we're looking for 3, 3, what happens now?
constant time.
Mm-hmm.
You will have constant time at the top.
For each list, right? So, the time complexity would be like the number of groups instead of all elements. That shortens it. So, this this makes it like one way to represent these groups, but the search complexity is what becomes the search complexity now. So we look for 3, 3, which we look for 3, 3 first. The time complexity for that would be the number of groups. Let's call it G. And the number of elements, let's call it N. And the number of elements per group, let's call it, I don't know, N, I guess. This is relative, so it depends on the size of which group we're working on. So, like in terms of this, what would be the time complexity of checking if like the elements belong in the same group? Of G, but how about searching for 3, 3?
You would have actually OG, and then when we find it in the G element, we just do the lookup there again.
Yes. So O of G would be, yeah, exactly. So you search for 3, 3 in a group, and then when you find it, you do the constant lookup using a set, makes it O of G, right? So the only thing you're depending on is going to be the length of elements. So does that make sense? Like, does anyone understand why the time complexity of lookup would be O of G? Why is it O of G? Maybe. I really can't hear, I'm sorry. Lookup time would be of 1 in each state. Yes, so worst case you go through all the groups and check, like even think of it like you try all the groups and check if both of them exist in that group. You don't even need to look for one initially and look for the next one afterwards. Does that make sense? I'm seeing nothing. Do you have any questions, by the way? Like, I want to point out the questions. Okay, so I have a question. What would be the space complexity? Someone who hasn't been interacting. Salah.
we'll be adding another set to each element.
In terms of these.
It's going to be all three for every set.
Mhm.
It's going to be, we have a list that contains the number of disjoint sets. That'll be all three. And for each element in each set,
Mhm.
and it's going to be about
Right. Overall, though, totally.
so three, that would be all three. 9 of them.
Yeah, but what would be G times M? N, right? Like the total number of elements. So we're having one entry for each element in the island, right? That's fine. So the time, this would be the time complexity of G time and of N space. Does that make sense? Let's consider one scenario where, what if we modified? So what if we wanted to add an edge between two nodes? So let's say in this case we're considering these are like unintersecting elements, right? So what if we said maybe the rules changed and maybe like diagonals also count as neighbors, right? I'm not sure if we have diagonals in this one. Like maybe 1, 1 and 2, 2 are diagonals, right?
This is 8 directional, right?
Like what if we made it 8 directional? Like in that case, these two belong in the same group, right? In a graph, normally you just have nodes and you just add edges between them, right? But in this case, it's a grid, so adding one more edge would be like considering another direction. We're considering these 4 directions. What if we also consider this direction? Does that make sense? So what would be like the modification cost? Brooke, what do you think would happen like if you were to modify this? Because diagonals have to be in the same group now. So far we know 1, 1 and 2, 2 are diagonals. And what else is diagonals? 2, 2 and 3, 3 are like is C4 diagonals with anyone? It's not, right? So maybe like let's ignore this for now. Let's make it 5, 3. So that we won't interfere with other guys. For now, let's just consider these guys. So you guys can see this side. So now we're considering diagonals as neighbors instead of just 4 directions. So the set of the islands has to change, right? So what do we do now? What kind of approach would you take to modify the set to encompass to take care of these changes, I guess? So the one thing that's different right now is that 2, 2 is diagonals with 1, 1, so it belongs in this group, right? Right? So all we know is there's a new edge between 1, 1 and 2, 2 that we need to include into this system. How do we handle that? Like an addition of an edge.
We're supposed to build the new set with just this, or do we have the island mapped again?
What?
Do we have the island mapped again, or are we
No,
supposed to
just
do it all?
like this is the like you already know 1, 1 and 2, 2 are the only ones that are supposed to be merged. Like you already know of the modification, and you know the only change that happens is between 1, 1 and 2, 2. So you want to merge those two. Like you don't know that they're in the same island already. Maybe they could have been. You don't know. But now you're gonna have to check. Like what would you say?
Instead of making 4 directional layers, we can have the diagonals
Uh-huh.
as a number. So if the area is constant, it's not that much.
Okay, that makes sense. Like initially, when you're loading it initially, you could have handled that. But what if this was already given to you? and you have to make the modification now.
Okay, so you go ahead.
I probably can see the size of the second component, which is 2, 2, and the first component.
First, you have to look up where they belong, right?
Yeah.
First, you have to see like 1, 1 belongs to this group, and 2, 2 belongs to a different group, right?
Yeah.
So now they have to be merged.
So, the merge cost would be lower if you put smaller size set into the bigger size set.
Right? What would be the time complexity of merging these? Like making this modification?
So the smaller size set size.
Yeah. So you take each element and you add it to this set, right? Like imagine the complexity that would arise though, like having to figure out which set I have to find, and I have to add it. You guys understand what's happening here? I'm trying to show you how, like, what are the drawbacks of using such a method instead of. This is technically a disjoint set approach, but like when you're trying to make checks and when you're trying to make like modifications, it's not as easy, I guess. Like it's not as efficient. Does anyone have questions on this, by the way? I'm gonna move to the next thing otherwise.
What will be the time complexity of merging two sets here?
Yeah, merging two sets, what he just said is you can find whichever set's smaller, you just iterate over it and add the elements to the bigger set. Right? So the time complexity would be O of the small one. Or whichever one you pick. Really, you can do the bigger one too. I mean, why would you pick the bigger one?
But how are you going to find the 2, 2, for example? First, you should find 2, 2. Right?
Yes, exactly. So the merging is just that.
This is just merging.
Yeah, so O of G is for the merging.
G.
Yeah, G being like the number of groups.
Don't we have to check, like, for example, starting from the first element in the first set, then the other sets, second and the other sets, third and the other sets? I think this is what we have to do, right?
When you don't know which edges are going to be added, yeah.
Okay.
But now we know that 1, 1 and 2, 2 are.
Okay.
That's why. Like if you don't know which have to be added, like this is actually a good point. Like when you don't know 1, 1 and 2, 2 are the ones that have to be merged. Now we're considering the fact that diagonals are the new rule, and we need to find the diagonals. So is 0, 0 diagonals with anyone else in a different group? And is it like doing that check may even make it worse? But like I'm even making it easier in terms of this. Does that make sense? But like you don't really need to ignore it. That's a lot of processing, I guess. So in this case, the modification means the search and the grouping or merging. So you search for the two groups, and then you merge those two groups. Right? If they belong to the same group, then there's no merging needed. Right? Okay. Any questions? Any other questions?
And lastly, in order not to face with such problem, we should start with the 8 direction directly, right?
Yeah.
Building this from the beginning.
Yeah. Like if you started building it from the beginning, this won't be a problem. Now my point is the creation seems reasonable, right? Like you do a DFS code and it creates this for you easily. Right? The time complexity or space complexity would be the same as you'd have for regular DFS. But when you try to do the checks and when you try to do modifications to it, that's when it's difficult. Does that make sense? Okay. Any other questions? Going once, going twice, going 3 times, going 4 times, and 5 times. Okay. Let's see another way of how we can handle such. How we can represent this. Like, I'm not going to modify too much, but let's see. This could still be better. Now, what do you know about these different groups? Like they're sets, right? Like the different groups are represented as sets. And we know that this is an undirected graph. Right? We were under the assumption, like we started the question saying that this is an undirected graph. Since these are grids, we can go in either direction. Right? What, like them belonging in the same group of an undirected graph, what does it mean? So starting from 1, 0, which ones can I reach?
Oh,
All of them, right?
all in the
All of them in the same group. So the concept of being in the same group of an undirected graph means starting from any of them, you can reach all of them, right? Since they're already in the same group, starting from any point, if you do DFS, you can reach to all of them. You can traverse the whole group, right? Like that's what you did, right? You found a starting point and you did DFS on it and then collected all the groups. So by definition, they're the ones you could reach from one starting point. My point here is, it doesn't matter where you start from, whichever one you can start from, the group is going to be reachable from that one. For undirected graph. Like all our discussions we're going to be making is on the assumption of undirected graphs. So like bear with me on that. Does that make sense? Alright? Okay. What if I nominate some guy, it doesn't matter which one it is, since they're all the same, like from 1 you can reach all of them. What if I nominate some guy, let's call it 1, 0 for this one, as the leader of the group. That's fine. And for this one, this is just 2, so 2 would be the guy. For this one, let's call it. Actually, we can go back to the example that we had where we can call it 3, 4. Doesn't matter. Doesn't matter whichever one we find, right? What if we nominate that guy and he's going to be the parent for all of them? Like, let's say all these guys are going to be represented, like their group label is going to be the leader guy. Right? So instead of having the list of as a group, we represent their boss, I guess, their boss as their group. So the boss of this guy, like his group is the group owned by 1, 0, right? For this guy it's 1, 0. For this guy it's also 1, 0. Right? So it belongs to the same group as itself. For this guy it's also 1, 0. For this guy it's also 1, 0. Right? For this guy it's 2, 2. Do you guys understand what I just did? You have a question? Oh. I mean, it's not really anything to see, so it's fine. So instead of representing them as a list of sets, I'm representing them as a list of elements. Or pretty much this is better represented as a dictionary, right? Like this guy is the key and this guy is the value, right? So it doesn't matter what group they are, as long as they have their leader printed with them, that's what group they belong to. Does that make sense? So let's store it as a dictionary maybe, right? A dictionary of leader. The leader dictionary where, actually I need some space. Who's the leader of 0, 0? Huh? 1, 0. Who's the leader of 2, 2 maybe? It doesn't matter what order they're in, right? Well, 2, 2. Who's the leader of 3, 3? The leader of 1, 1? 1, 0. The leader of 1, 0, I guess would still be 1, 0. And so on. You get the point, right? I don't think there's enough space to write all of them. So, in this case, what would be the cost of checking? Like checking if two things belong to the same group. Constant time, right? So that takes care of this O of t time complexity that we have to go to the different lists. And do you guys understand why the checking is going to be constant? So let's take an example of, we are supposed to check if 1, 1, if 1, 1 and let's say 0, 1 are in the same group. Like what's going to be our action? You know, What do you do if you want to check if they belong to the same group?
So I'll check their leader.
Yeah, if they have the same leader, then they have the same group, right? So this would be a constant time check. Like this improves of G, right? And in terms of space complexity, what's changing? Nothing, right? So we're not changing the space complexity, but we've improved the time complexity for searching. That's better. Okay. Let's see. Anything I'm missing? Okay. How do you know who's the leader? How do you know if a node is a leader? Let's say you're given 3, How do you know if it's a leader?
Checking the values. Checking if it exists in the values.
It does exist in the values, but how do you know it's a leader?
Checking its leader.
Oh, its value has to be itself. Like its leader has to be itself, right? If it's a leader of the group. Does that make sense? Yeah, that's a good point. So if I check for 3 and its leader is 3 then it's not itself leader, right? So there's another leader that handles this. Does that make sense? So let's get back to the scenario where we considered modification. This time where we have to merge 2 and 1 So the new edge between 2 and 1 is being created, right? What do we have to do now? What thing can you do? I don't know. Doesn't matter. Don't worry about the efficiencies. Huh? What? The leader? Who's leader? So for 2, the leader is 2. For 1, the leader is 1, 0. What do you do? So the leader of 1, is 1, 0. You give it to 2, right? Oh, so this has to be 2. Okay, makes sense. So this guy becomes 2. Right? Since they belong to the same group, so they all report to 2, right? But what about the other guys? Like the other guys that are grouped in 1, 0. Like whose leader was 1, 0? Like 0, 0 and 1, 0, etc. Like they also belong with the group as 2, right? A what? Huh? Okay, so what you're proposing is for all the elements, so now before we change this, their leader is 1, 0, right? So for, like let's say you're merging, like you're merging this guy under this guy, right? Like you're assuming whatever is the leader of this guy is becoming the leader of this guy, right? So you're merging those two groups. The groups are represented by leaders. So if both groups are being merged, then their leaders have to be 1, right? You have to nominate one leader for both of them. So let's say you pick the leader of 2. Doesn't matter. You don't know anything about 2. You just pick whoever is the leader of 2. So you're supposed to assign that to all the nodes that have 1, 0 as their leader, right? So we insert 2 and 1, right? So what we want to do is not really merge 2 and 1, but merge the groups of 2 and 1. And what are the groups represented by? Leaders, right? So we want to work on the leaders, not the groups. And we do want to work on the groups, but the leaders are what we want to emphasize on. So for the leaders in this case are 2, 2 and 1, 0, right? So the group represented by 2, 2 has to be merged with the group represented by 1, 0. One thing you can do is iterate over all the elements that are in 1, 0 or 2, 2, doesn't matter which one you pick. Iterate over all of those elements and change their leader to 2, 2. Does that make sense? What would be the time complexity for that?
Number of leaders of 1, 0.
Number of elements
Yeah.
in that group, right? So number of elements would be m, like m of 1, 0, right? Number of elements in the group 1, 0.
But it could go more because we can't really know the leader unless we go all
Yes,
over the elements.
exactly. In that case, the number of n would be like this. Okay. So, why is it of n? Like, do you guys understand why it's of n? We're going through the whole array to find elements that are of group 1, 0 and modifying them to be 2, 2, right? Of n, where n is all of the elements. Does that make sense? Which means it doesn't matter which one we pick, we're going to have to go through the whole list and find those who have the leader of 1, 0 and then modify their leader to become 2, 2. That's fine?
Yeah. What if we have also another map where the keys are leaders and the values are the children?
The leaders and their
Then we
children.
don't have to.
That's fine, yeah. That makes sense too, I guess, right? So in that case, our time complexity would be of m, right?
Yeah.
Where m is. So what Suha proposed is additional to this. What if we have children dictionary for each leader? Where how many leaders do we have here? 1, 0 is a leader, and it has children of 0, 0 and 1, 1. And
0.
yeah, like we can assume this are part of the group. Then another list for 2, 2 would become it's just 2, 2, right? And C4 would have C3 and C4. That makes sense? So, in this case, what we have to do is instead of iterating through all of them, we can just iterate through the children of 1, 0 as well. But this one would have to have like extra space used, plus when we merge the group of 2, 2 and 1, 0, we need to remove the entry of 1, 0, and we need to add all these children to 2, 2 as well. And there's a lot of modification that goes on. And keeping track of the dictionaries is not going to be as easy. That's fine, right? But what if, like I'd suggest, what if instead of just changing all of them, what if you only change the leader's leader? So, what if we make it hierarchical instead of iterative, I guess? So, let me get rid of this so that it won't be confusing. I do want to ask one random person, right? Like, what are we doing right now? Like, when we're trying to merge 2, 2 and 1, 0? Leaders of who? Of?
Of the, let's say 2 leaders.
Yeah, one of the leaders, right? Like, if we say 1, 0, whoever his group is, like all the elements have to have a different parent. But what if their parent also had a parent, and parent is not a constant check? Like we said, checking for the parent is O of 1, right? What if we sacrifice that and we make it a chain of parents? So instead of modifying the leaders of 2, 2 and 1, 0, like instead of modifying the children of 2, 2 and 1, 0, or one of them, what if we just went to the leader straight and we modify its leader to 2, 2? Does that make sense? So what would be the leader of 0, 0 in this case? 1, 0, right? But 1, 0 also has a different leader. It has to go to 2, 2. But 2, 2, does it have a leader or not? How do we know that it's the final leader? Exactly. So what if the check for the lookup for leader, it's not constant check of which element is my value like in the dictionary, but just iterate, like recursing until we find the absolute leader of that group. Does that make sense? So they chain up in some way like this. So 1 0 has its members 1 0, 1 1, and so, right? 0 0 and stuff. 2 2 has a group. Actually, we don't need 1 0. 1 0 is part of the group itself, so it's not a relation. Like we can assume a group is the list of nodes that a node can reach, right? If a leader can reach them, then they're part of its group. So 2 2 is a group of its own, and now we're merging 2 2 and 1 0. So what if we just added an edge to 2 2 and 2 2 becomes the new leader? So what these guys know is that 1 0 is their leader. What this guys know is 1 0 is the leader. But 1 0 knows that 2 2 is the new leader, right? So when 1 1 checks, it's not just going to take 1 0, but whatever 1 0 returns him as the absolute leader. So we can recursively keep going until we find the leader of a node is itself. Does that make sense? Do you guys understand what's happening here?
Yes, so you can go through the whole thing.
We're gonna have to go through like the whole tree. We're not gonna have, for instance, when we're trying to check if 1 1 and 2 2 belong in the same group, we're gonna find the group, the parent of 1 1, like the ultimate leader of 1 1 and the ultimate leader of 2 2. Finding the ultimate leader, it's a calculation of iterating through the tree and like finding the absolute leader, like finding the top. So it kind of becomes a branch of things. So what if we added a new node? Like what if we find a new node? Let's say, I know this doesn't apply, but let me see. Yeah, let's say there's 1 2, a new node that's related to this, and we know it's got a relation with 1 1, right? Right? So we say 1 2 and 1 1 are related since they're 4 directional neighbors in the example. Are you guys confused yet? Are you following what I'm saying? So if we add 1 2 as part of the element and we say it's a neighbor of 1 1, what we know is that 1 1 has a new neighbor called 1 2 that's valid for this group, right? So we just add 1 2 and 1 1 3, like 1 2. Now, we don't really do this necessarily since what we want to do is put 1 2 in the group of 1 1, right? Right? So we can just assign it to its group leader and not necessarily to just 1 1. But even 1 1 doesn't know like the absolute leader. But when it calls for the absolute leader, it can just keep recursively calling and return 2 2, right? So the leader of 1 2 is going to have to be 2 2. And like even though we added it to 1 1, 1 1 doesn't realize that the direct leader is 1 0, since it can recursively call to the absolute leader. 1 2 can be added here as part of the group. So it's kind of becoming a branched thing. Like it keeps branching up until like when we add more, it can be 2 5 or whatever. After we branched it all, what if we decide to again merge 3 3 and 2 2? In that case, like 2 2 would have to report 2 3 4, right? Like the leader of that group, and also 3 3 reports to that. Like, are you seeing the tree structure here? I can redraw this again. So let's say in this case, 3 4 is the new leader, any absolute leader, 3 3. Also 2 2 also reports to that guy, and 2 5. Let's call it. It doesn't matter. I'm not going by the logic of the question at this point. I'm just adding new nodes. 1 2. Are you seeing the tree structure in this? So initially what we had is nodes like 1 1 and 0 0 that report to 1 0, right? Then we decided to add 2 2 to the group, and we chose for some silly reason we assumed 2 2 should be the new absolute leader, right? Obviously, like 2, 2 would have been better off just being added as part of it, but we didn't know that, we just chose 2, 2. So we assigned the leader of 1, 0 to be 2, 2. Right? And we wanted to add 1, 2 again, to as an edge of 1, 1. So 1, 1 reports to its leader, so another member wants to join the group, so please add him to your group. Now, adding it here would not be the most efficient way we do it, right? Like all we need to know is that it needs to be in the group, right? So why not just add it to the top leader? It doesn't matter where it's added, it's just more efficient for him to check its leader. Right? So we added 2, 2, 2. Like another 2, 5 maybe added, same logic comes up. It really doesn't matter in this case. Sorry, I'm feeling bugged by this even. Okay, so, and then another new edge gets created that links 2, 2 with 3, 4, with 3, 3 actually. Right? So 3, 3 realizes that 2, 2 wants to join, like the group of 2, 2 wants to be merged with 3, 4. Okay, so before we left, before lunch, we discussed about the 2 functions that we'll be using in union-find algorithms, which is the union function and the find algorithm. The find function, the union function. The find function pretty much iterates over the tree and finds the absolute leader of the group, and the union function finds the absolute function of the absolute leader of 2 groups and merges those groups together. So this is pretty much like the most important code that's needed in union find algorithm. So this is the basics. This builds us the tree. And I also forgot to mention earlier, but I wanted to show you a visualization of how this runs. Can you guys see this, or do I need to zoom in? Can you guys see this now? Maybe on the share screen? You can see it? Okay. So, what happens is we're given a list of nodes from 0 to 15. Right? You can see this. And we're trying to build a union set data structure, I guess. A disjoint set data structure for this inputs. So, like I said before, we instantiate them with nothing, I guess, no parent, which means they'll have to be the parents of themselves. So, what do you think finding 2 would give me? Does this make sense? So, finding 2 gives me the parent of 2 in this case. So, I guess like in this example, it's using -1 as the initial state, but we can use themselves because each of those elements can belong to like their own group, a group of their own, where they don't need to be in a group. So the first thing I need to do is let's start with an example that we want to build. So let's say we have a node. So it's numbers from 0 to 50. Let's just consider the first 5, and let's say there's 0, there's 1, there's 2, there's 3, there's 4, and 5. This is fine, right? So, I don't know, I'm just creating random edges to each of them, undirected edges. Do we want one to be empty? Okay, let's see. I'm not sure how to handle single elements, but let's see. Okay. In this case, what it's assuming is -1. Like we discussed that we know the leader by checking if the value of that element is the key and the value are the same, right, in the dictionary. But this one, it's considering -1 is the value instead of itself. So anything that has -1 is the leader. Does that make sense? So that's the only difference here. That's why it's always -1. So nodes that are -1 are unconnected nodes that like they're presented on the screen. So from 0 to 15, I guess, and they just have -1 in their dictionaries. So they'd be the leaders of their own group. So in this case, we haven't enabled path compression or like the other anything else. So we're just going to discover the find and the union function. So find gives us the leader of 2, which is itself. So since it's -1, and let's try to unite the first element. So 1 is it alone, so it doesn't really need to be united with anyone. So we can unite. There's an edge between 0 and 2, right? So let's unite 0 and 2 and see what it does. So it finds the leader of 2, finds the leader of 0, and it assigns 0 to be the leader of 2. So by this algorithm, the first one is to be it assigns 2 to be the leader of 0. So on the zeros index, it's giving 2 as the leader. Does that make sense? You guys can read out the edges I need to enter, maybe. Somebody? I don't want to look back. 3 and 5. Right? So I unite them, so it finds the leader of 3, finds the leader of 5, it merges them together, and then 5 becomes the leader of 3, or the group that has 3. Anything else? 4 and 2? It finds the leader of 4, it finds the leader of 2, which is 2 itself, it merges them together, and 2 becomes the new node, the leader. You do realize, like, it's the pattern so far is it's making the second element, like I'm inputting 2 things up. The second element, the leader, like the leader of the second element to be the leader, right? Okay, anything else I need to add? This is it for now, right? So what do you think happens if I put 2 and 8, or 4 and 8? Anyone? What do you think happens?
8 would be parent of 4.
8 would be a parent of 4? Would it though? Like, who's the parent of 4 now? So wouldn't 2 be the parent of 4 would have a parent that's 8, right? Like, we're only working on the parents. So first it has to find the parent of 4, it has to find the parent of 8, and then now those are the ones that get merged. So we're only working on the parents. So when we're merging the groups, not the specific individuals. So the group is represented by the parents or the leaders. So we're only caring about the parents when we're doing merges.
So when it joins 4 with 2 and 0, it didn't assign 4 to be the new leader, but now it's assigning 8 to be the new leader.
Like I said, it's taking, like, so far the pattern seems like it's taking the second input to be the leader.
But when 4 joined 0 and 2, 4 didn't.
Yeah, we put 2 afterwards. We put it like 4 and 2, so whatever is the leader of 2 becomes the new boss.
So you said the second one. So the second one is the 4, newcoming.
No.
This one, the newcoming is 8, right?
I don't mean by second one, I mean the one we inputted second. I don't mean the one that's newcomer. Like on the input, on the top. Does that make sense?
Yeah, but you put. So you put 4 first in
4 first and then 2 second. So the convention here is that the first element goes under the second element. Does that make sense? I mean, this obviously has the issue of building a chain, so it could be something like, if the second element is always going to be the boss, I can make it 7 and 6. So actually 6 and 7 make more sense. 6 and 7. So I want 7 to be the boss of 6. I unite them, 7 becomes the boss of 6, right? So I can keep doing this. So 9 can join in, and I can do the same thing for 9. 6 has an edge with 9. Still doesn't matter, the second element would still have to be boss, and it keeps going on like this. So 6 or 7, it doesn't matter what I input here as long as it's in the group. But the second element is something new. Does this make sense? This is starting to become a chain, which is not good. So the find function for 6, by the way, the find function for 2 gets me 8, right? So it's just one chain. But the find function for 6, it's going to have to go all the way up to 10. It finds 7 and then finds 10, 9 and then 10. Now, it only returns 10 when it reaches the tree. So we don't want this. So there's optimizations we can do to avoid this. Does that make sense? You guys can play along with this. I can send you the link to the visualization later on. But for now, just I hope this helped, I guess. Okay. Do you have any questions about this? You guys have questions? No question. So we can jump into the question. Has anyone read the question? The question I sent to the group? There's been other text afterwards, so we need to stop. Okay. I guess maybe you can't read it, so let me read out the question and tell you what this means. Okay. So we are given an array of equations and inequalities. So there's a bunch of letters A, B, C, D, E, F. It doesn't matter, and they have relationship in that they could be equal to each other or not equal to each other. The challenge here is to figure out if it's a valid set of equations or it's not a valid set of equations. Meaning, so let me run with an example. I hope you guys can see the shared screen as well. So the first example says A equals to B. A equals to B, and A is not equal to B. Right? Does this make sense? Like logically, is this right? It's not right, right? So in this case, we return false. And the second example says, okay. Second example is A equals to B, B equals to C, A equals to C. Does this make sense? Like, is there any fallacy with this? What about if this was the case? Does it make sense? Why doesn't it make sense? I don't know. If A equals to B and B equals to C, then it's conflicting, right? So, do you have any questions about the question, by the way? Anything that's not clear? So you're given a set of equalities and inequalities, and you're supposed to validate if it's valid or not. Like a combination of them makes sense or not, right? So tell me what scenarios make it false. In what case would it be false? Like what's the case that makes it invalid? So if I have a list that's all equalities and no inequalities, would there be a chance of it being invalid? Or maybe if it's all inequalities and no equalities? So what's making it invalid? So when we find something that's equal and we find an equality that makes a fallacy of it, or vice versa, right? So how do we know that A is supposed to be equal to C in this case?
There are items that are supposed to be equal to A, one of them is B,
Yes.
and C is supposed to be equal to one of those items, which is B specifically, and A. So since A has to be equal to C, and certain
Yes. This is, by the way, some question. I never did this question in Disjoint Set, so my vagueness. Okay, so we've already established that B is in the same group as C. Like B is the same thing as C, and A is also the same thing as B. So they belong to the same thing. But here, this implies that they don't belong to the same thing, right? So this makes a fallacy of what we've already established. So if A belongs to the same group as B, so who belongs in that group in this case? So there's a group that contains A, there's a group that contains B, there's a group that contains C. The relationship is equality, but what it's giving us is the fact that they're the same thing, right? Do you guys see how this is a graph question, by the way? Should maybe we discuss that first? Like, do you see how this is a graph question? Or right? You see how this is a graph question? So these are the different nodes. A, B, and C are the different nodes. Their relationship would be the edges, right? So A is related to B. So which one do you want to be the valid relation which we consider? We can consider equality or inequality. It really doesn't matter which one we pick. You guys pick. Equality, right? So two nodes are equal means they're related. That's fine? Okay. They're related means they have an edge between them. That's fine? Okay. So equality means they have an edge between them. That's fine, right? So A has an edge with B and B has an edge with C. Right? So we build the structure like this. So we know that A, B, and C belong to the same group because they're related. Like they're in the same set pretty much. Right? So if they have a relationship and that relationship is equality, then everyone is equal to everyone. Right? So at any point if you find someone from that group unequal to someone else from the same group, then that's going to be a fallacy, right? That's the only case when it's going to be valid. So things of the same group, thinking they need to belong to a different group. They're confused. Okay, does that make sense? So do you guys see how this could be a union find problem? What do you think? Like, any opinions? Good?
If we join or if we build a graph for the equality with one structure and for the other structure, if we build for the equality, if there is an element in if there is a union in what spaces
Invalid, I guess, but how would we, like how could we leverage the powers of union find for this question is my question.
Yeah, you can use.
Like in union find, we said we would use the two main functions: the union function, which merges two groups, and the find function, which finds which group something belongs to. Right? That's my point. Like how would you explain it in those terms?
So first,
Yeah. Okay. Do you want to speak? Go on. Pierre, if you want to say, or he raised his hand, that's why I pointed to.
Whenever we find equalities, you can use the joint function
Mm-hmm.
and create a graph.
Mm-hmm.
Whenever we find inequalities, you can use the find function to see if the elements are in a graph.
In the same group. Did you guys hear what he said? Did you? This makes sense? So, to rephrase it, what he said is, like we discussed before how we can turn a graph like this into a set of groups, right? Using union find. Using the union function, we can build this. And using the find function, we can check if two elements belong to the same group. So, for equalities, we can build this. Like we can build the group set, right? And for inequalities, we can check if they belong to the same group, and if they do belong to the same group, and inequality means they don't want to belong to the same group, right? If they do belong to the same group and they don't want to belong to the same group, then we can return false then. Does that make sense? Okay. We discussed what's one of the problems that we faced with this algorithm. Like what's the weirdest thing? Anyone can point out something that's not efficient? Like, so what's the inefficient part of unifying algorithm like this?
Randomly pick the new leader from two groups.
That's one. So like the finding is what's taken too long.
Yeah, that's still making one group the leader of other one still inside the set. So
I think finding the leader is the problem. Right? So you find the leaders and then just after that, though you don't really do anything, you just assign one to the other. Do you get my point though?
but aren't we randomly in the make union function making one leader the other?
Yes. But when we're doing that, what's taking long is when we're trying to find its
I
leader.
see. I'm thinking about it.
Yeah. In general, of course, the union depends on the find, so it's going to be inefficient.
I see.
Do you guys understand? Like the find function is not being efficient because it has to iteratively call for, like its parent, I guess. So, let's stick with this case. Remember this graph, right? So these elements belong together. These elements belong together. these elements belong together. So let's, for the sake of this argument, let's take this one only, and their union find, like their what is it called? The disjoint set 3 would look something like this: 4 and 0, right? This reasonable? Like we can have more elements onto them, right? Like we can actually go back to the example that we had in the 3. And there's also 8 on top. So, finding the leader for 4, what's going to be the process? Got it. What's going to be the process to find the leader for 4? You go through what? The ancestor to it, right? So the parent of this, and the parent of this, and the parent of that, right? But, like, for all the elements, and there's also one more example that has 6, 7, 9, and 10, right? I'm just copying it from the visualization I showed you guys. Right? The ancestor for 6 means going from here to here, from here to here, from here to here. Right? But we know, like, every person in the path, they all have the parent of 10. Does that make sense? So what if, like, while we go through a path and then we assign all of them to 10? Like when we're finding. So it could be 10, and then 6, 7, 9. That's it. Wouldn't that make it a better find function for later? That makes sense, right? So that's one thing one optimization we can do, that's called path compression. So when we're going through a path, we compress it in that since they all report to one super leader anyways, why not just directly assign them to that one? So that's what happens. But let me show you, can you guys see the slides maybe? So for path compression, I hope you guys can see the code, but that's the only modification that needs to be done. Can anyone explain to me why this works to compress everything? Like what does that code do? Anyone? Huh? It does call the recursion though. Like what change does this code do? Like the only change is parent of v equals to the recursion instead of just returning it. So it's also assigning without returning. So what's this doing? So in this example, for instance, 6, 7, 9, 10, what's this code going to do? Like when I call a find function for 6, what's going to be the new output of the tree? Anyone? No, just tell me. This is the tree right now, right? I could find function on 6. What happens? It returns 10. But what modification does it do?
It will assign it as parent 6.
It will assign what?
It will assign 10 as a head to 6.
So 10 is going to be the parent to 6, like this? Like this? Huh? So
6 will cause
huh?
6
Okay, let's roll back now. Okay. I think it should still work. 6 will call the function on 7, and 7 will call the function on 10, and 10 calls the function on 7. So this returns 10, right? So 9, what happens to 9? It will return 10, but what does it do? The modification it does, like in the code, before it returns. Parents of v has to become the parent that's getting, right?
Yeah.
So the parent of 9 is going to have to be 10. In this case, it's fine, right? So how about 7?
7 will assign 15 and return to 6.
So the parent of this guy would have to be 10, yeah. So this will disappear and then this will happen. Okay, so then it returns there, right? How about this guy? Yeah, 6 would have to do that. Does this make sense? Like with just a little modification to it, we can compress the algorithm to do this while finding it. So everything on the path will be compressed to the top. Does that make sense? Like how would that reduce our time complexity for find?